In video 29 on the Foundations of Computational Economics course, we will be coding up the Rust model of bus engine replacement. So this is a practical video. Let's start by reviewing all of the main equations that we will have to put into code. Remember that the final version of the engine replacement model with the error terms is expressed as the Bellman Equation or Bellman Operator in the expected value function space, which is denoted EV of x and d. This is the operator that we need to code up. And let's think about how to represent these functions on a computer. So first of all, the state space, x, is given by the grid with endpoints. And because we will be working with bins of mileage, we don't really need to know the mileage values. All we need to know, and we can work with, just the indices of the bins. Now, d is either 0 or 1, and this is a replacement choice. So EV of xd should be or can be represented by a matrix of n by 2. Okay. The instantaneous payoffs are given by the negative of the costs, where c is the maintenance cost function, and we will use the specification from the Rust 1987 paper, which has this arbitrary or normalizing multiplier. It actually should be plus here, I believe. And then there's one preference parameter. Yeah, I think this is a typo. All right. Now, the mileage process is discretized, and the transitions are described by the two transition probability matrices. One corresponds to the no replacement decision, and the other corresponds to the replacement decision. All right, so we'll need to have these. And then converting the problem into the Bellman Operator version, we can see that the Bellman Operator has the same functional form as what we saw in the second slide, but this allows us to run the VFI algorithm. So we will start at arbitrary guess of the expected value function. We will apply this operator and then continue applying the operator until we converge uniformly. So this basically is the successive approximation solver that we need to use, and we can reuse the code from what we had before. Yeah, that's about it. Okay, one more thing. So it's always very useful to examine the structure of the problem before starting to write the code. Examine and think about what other ways to simplify the code potentially. And here, the important thing is that once the engine is replaced, then it's the same thing as having the new engine to start with. So the expected value at any point x of replacement is the same as the expected value of zeroth bin, the initial bin of mileage with keeping decision. It's actually not that hard to see this. Let's just go back to the expression for the EV, for the expected value, and let's plug 0 and 1, 0 and 0, so the new engine, and we're keeping it. We can see that x and d only enter in here. Well, this d, that's the argument of the deterministic part of the choice-specific value function, and we have to call it with 0 and 1 in the log sum expression. This x prime is something different, so really x and d only enter through the transition probability equation, or transition probability matrix. And then, of course, looking at this two matrices, we see that this first row here is exactly the same first, or any, in fact, any row in this matrix. But we can conclude that the expected value of replacement is the same as the expected value of keeping the new bus. And if you think about that, that makes a lot of sense. So it doesn't matter how many miles are on the bus when we replace it. From the point of view of the model, it becomes a new bus which we can keep. What it means for the code is that instead of having two different EVs for different Ds, we can just work with one vector of the expected value, which only depends on X, and use its first component to describe the expected value of the replacement of the bus of any mileage, right? So this is very handy. So now we can have EV, the expected value, is just one vector. And then, of course, we only need one transition probability matrix. We don't need both of them because we will use the first row of the keep transition probability matrix as the in place to describe the new buses. Now, the second one more thing has to do with the numerical stability of the calculation. We will have to compute the log sum function, which is given by the log of the sum of the expectations of the deterministic parts of the expected value functions. Or I mean, we can just refer to this as expected value functions, keeping in mind that it's the deterministic part. Anyway, so this involves calculating the exponents of potentially large numbers, and this is definitely the source of a worry. So the standard way to deal with this is to know that we have this equivalence. We can just take a constant out of the values under the exponents, and it will show up as the constant that needs to be added to the log sum function on the outside. You can readily verify that this, this is equivalent to this. And what is a good choice for the m? Well, because the exponent of the negative number is always below 1, we can have a very simple upper bound on this each of the exponents by just equating m to the maximum of the two numbers that we have to put into the log sum. Okay, so these are all the preliminary points that I want to make, and let's start coding. And we are nicely given the standard parameters in the init formula here before we can start writing any code. Okay, so let's maybe add some doc strings here for the circular model object. What do we have to do? So let's start with an assert. I want to make sure that this p's that are given, the transition probability parameters, I'm sorry, it should be just p, they're less than equal than 1. So their sum is less than or equal than 1. It is traditionally set up with this model that you don't really need to give it a distribution, because the remaining member of the distribution can be calculated. So let's say here probability. No, I transition probability parameters must sum up to less than 1. Okay, and then we just want to save the parameters that are given into the object itself. So we have to say self n equals n, and let me just do it in one line here. RC C P and beta. RC C P and beta. As you remember, this is sort of like a Pythonian way to assign a bunch of variables in one line. And what happens is that actually this is converted into a tuple, or it's understood as a tuple without the brackets, which is possible. And same thing here. And so this is an equality of two tuples. As we will be working with the grid of this problem, it's convenient to make a grid right away. And we have 175 bins. A range will produce a list of integers from 0 to n-1 that can serve as a grid. And then it would be also nice to calculate the transition probabilities. And let's write a separate function for that. Transition probs. I made it double underscore to signify that this shouldn't be accessed from the outside of the class. Right, so, and then we can have it here. What should it be? Yeah, it doesn't need any arguments, right? Because it can just grab them from the object itself. Matrix. Okay, so let's pass for now. I see one problem. So imagine that we change the size of the engine replacement model later on. So we change n. Can we do that? Yeah, we can. We can say model equals Zerker. Let's print model, and let's say model.n is now 10. Actually, let me switch to the normal notebook view. NP is not defined. Oh, yeah, we forgot to import numpy's NP. But one was given. Transition takes 0 positional arguments, but one was given. Which one? Self. Wait a second. That's supposed to be... Yeah, I forgot self in here. Print model, print something pretty strange. Let's make a wrapper. What should we say? Can we say Rust model? Keep switching between Zerker and Rust. I think it's Rust model. Let's just give it. Let's just return the ID. Remember, ID is the unique identifier for the object, so like memory location. We can say ID of self to calculate that, and yeah, there we go. Is it hex? I think it should be hex address, but it doesn't matter. We can treat this ID as just an integer. It's a unique identifier and it can be expressed as an integer. Fine. So we know it's a Rust model now. I mean, in the representation, we could also export all the parameters and other things as we did before, but let me save some time now for typing that. Okay, so what I wanted to say is that now, once we changed n, that's completely possible. The grid didn't change. So model grid will still be a grid up to 74, even though now n is 10. And so the good way to do it is to try to update everything that depends on these parameters as they are changed. And the right way to do it has to do with writing special functions for property setters and getters. And let's look at that. I don't think we've done that before. So let me just Google Python attribute setter Stack Overflow. There we go. Pythonic way to use getters and setters, and here's a nice example here that we can work off. So what happens is that we have to say the property name as a function. So, for example, n is going to be sort of like a method. Attribute getter for n. It's a lot of additional work, but let's see where it gets us. And we have to use this decorator for the function to say it's actually a property, and so it can be used as a property with the dot n notation instead of dot n with brackets, as we would have to do for the method. And this would just return self. And let's say there is an internal n. The internal n is going to be the property that should be hidden from the outside world. And this is always equal to n, and this is where we will save it when we allow it to be set. And this is how that's done. So we will have property n setter with a function def n self value. So we now this will be called every time an n is assigned something. All right. Let's just print n is assigned some value. And let's see what happens. Look, n is assigned 175, n is assigned 10. Let me not print this grid. So when is this happening? The n is assigned 175. Well, that happens right here. Self.n equals n, and n is defaulted to 175. So even when we assign from within the class, this setter is invoked. And therefore, it's ideal place to create the grid and the transition probability. Because now, even if we later on change n to something else, to 10, then again this code here will be called, and the grid of the model object and the transition probabilities will be updated. But I guess we should first save the underscore n equals value here. And now we can use self underscore n as actual n. Okay, what about transition probability? So remember, we need to create something like this, the transition probability matrix. Because we will use the trick and have expected value saved on in just one vector, then we can use this first row of this transition probability matrix to represent this one. So we only really need one. Let's start creating this. So let's call TRPR, transition probability, and I'll start with zeros of which dimension? It needs to be self double underscore n. So the dimensions of the model. Let me test as I code. So print model TRPR. And this is going to be signed here. So let's not forget to return. So now what happens is that as we initialize model, n is set over here, then this is run, this is run, this is run, and in particular the transition probabilities are saved into this variable and returned, and then they are set to this self-trpr. And this is what I want to print. All right, there we are. These are zeros in one dimension, and I want them to be a matrix of n by n. Oh, bracket. Okay, here we are. Maybe let's look at the smaller problem. Yeah. So now I've set the n to 10 right from the start, and here's our small transition probability matrix. Now, remember there is this nice diag command in NumPy, and it creates the diagonal matrix with the that creates the diagonal matrix with a given vector on the diagonal. And then we can move this diagonal in question for k greater than 0 diagonals above the main diagonal, less than 0 diagonals below the main diagonal. So looking at this matrix, I'm thinking that that can be diagonal with several diagonals updated. So maybe I don't even need zeros. I need diag. And then what do I put on the first main diagonal? On the main diagonal, I should put self p, right? Self p, the first value in this transition probability parameter. Well, maybe I can loop over them. Yeah, I guess that's what we need to do. Okay, go back to zeros. This is going to be initialization for the loop. And now for I in range of length of self p, I want to say trpr plus equals np diag. They are all zeros to start with. And now I need to give it a vector of n elements. So how do we do that? Well, now why should I go through indices? Let's just do a p, which will take values from this list. Okay, now I want p, but I need to multiply it so many times that there are values on the diagonal. So when I multiply here, I'm multiplying the I want to multiply the list. So I'll put p back into a list and multiply it to get a list. And diagonals should work with lists, right? So v is 2D array, return is a 2D array. I'm not sure it's going to work with the list, but let's try. No attribute p. This is interesting. So see, we're setting n before we're setting p, and that's why it doesn't see the property yet. So what if we do it this way? List object cannot be interpreted as integer. Where is this coming from? In the transition probabilities. All right, range shouldn't be there. Of course, that was a mistake. Okay, here we are. So we are taking the first 988. No, that's not right. It's just that we are adding to the first diagonal all the time. Okay. So I do need the index there. So I'll convert this into the enumerate. And enumerate, as you would remember, takes the values from this self P, but then also provides the index of each of the value. So K, from here, the diagonal, we should increment it according to the parameter, like so. Operands could not be broadcast together with shapes 10, 10, 11, 11, 10, 10. I guess what we need to do is we need to extend this. So one diagonal above the main will have one element less. So something like this then. Okay. So see what happened here is that we've taken P, made a list out of it, and multiplied it so many times to make a long list. But the length of this list must correspond to the length of the diagonal where we want to put it. And the first diagonal is the full n, but then one less, one less, one less, one less. Anyway, so this now has exactly what we need, except for one thing. Except that we don't know whether the rows sum up to 1. And to check for that, let me do this. We'll do the remainder of the unity. We will calculate the remainder that needs to be added in this one particular way. Now, I'm thinking something of too complicated. What we really need to do is we need self P, which is the list, and we need to add to it one more element. What's the element? That's 1 minus sum of self P. We already know it's not above 0, and we need a list out of this element. That's like a list with one element. It might be 0 if the sum of self P is equals to 0 exactly, but if it's less, then this element will solve our problem. It's invalid syntax where? This is the list. This is the list. This is the list. Numeration 1 extra bracket, I suppose. That didn't work all too well. So now I want to look at this list separately. So the list is this. So I guess it did work okay. It's just that the matrix now doesn't look like one. Let's give the model some easier to see transition probabilities. Staying with 0 miles, say 10%, 20, 50, like this. And another 10, say another 10. And the last one we don't really need. Okay, there we are. Ensure sum up to 1. We don't need this print anymore. Right, are we done or not? Look at the last row. It's just 0, 1. That's not good. And here it's not good. Here it's not good. So they don't sum up, although this first rows do. So the last step that we need to do after we've populated all these diagonals is we need to correct the last point, the last column. TRPR of everything in the last column should be equal 1 minus NP sum of TRPR every row and this should be 1, up to minus first column, and I want to sum up according to the first axis. Again, is there a way to avoid this? So what's going on here is that we want to put into the last column the remainder of 1 if we subtract the sum of all of the previous columns. Right? So for example, into here we would put 1 minus 0.1 plus 0.2 plus 0.5 plus 0.1. So the sum of these. And into 1 we should put the 1 minus the sum of all of the zeros. Well, all right, let's just leave it like this and instead simply check whether we get the correct stochastic matrix. So I want to print the sum, and as you can see, it's exactly right. So even though we get something that looks horrible as the transition matrix, like this, you know, almost 0 here. The rows sum up to 1 as they should. Now, what's the problem of this? If you remember our very first lecture, you know, the problem comes from the fact that 0.1 is not representable by the in binary arithmetic, or not representable all that well. So maybe by shifting this to some powers of 2, yay, then we get a nice picture. So no infinite series of binary point expansions. So what do we have here? Do we have the transition matrix as it should be? Looking down here, we get 1 and then 0.2, 0.8. So the last column is just the remainder of the row. And here it's 0.6 correctly, and this is 0.2. So we just ensure that, you know, the last column is the remainder of all of the columns to make sure that this is a stochastic matrix. This is clearly not a completely exact process, right? Because the bus, which had driven, you know, a mileage from the last bin, has only a chance to be driving the same number because of the upper bound of the problem. Well, this is the upper bound issue. The solution will be affected by the fact that we have to truncate the problem at some point. But presumably this upper bound is so large compared to the data that it's not going to be met, or it's not going to be restrictive at any point of us working with this model. Okay, so we are done with transition probability. And for the default parameters, we get the same, you know, the check passes, all the rows sum up, even though they don't look as nicely as this. What's the next thing to do? The next thing is we should code up the Bellman equation, or Bellman operator, in this model. What should be the input? It should be the expected value in the current period. I'm sorry, in the from the previous iteration. So let's call it EV0, and the return should be EV1. Which is like the operator applied to EV0. And we could also probably return the policy. What is the policy in this model with error terms? Well, the policy is the the choice probability to choose a particular action in the given point of space. Okay, so what should the Bellman equation do? Well, let's look at the formula here. We need to calculate the log sum function, and then multiply or calculate the expected log sum with the transition probabilities, appropriate transition probabilities. But the log sum has to be calculated for all values, possible values of x prime. So for all points on the grid, in other words. Let's start with this. So let me say x, that's going to be x prime. That's going to be self-grid. And we want to calculate the v's, right? So in order to calculate the log sum function, we need to have this v's of x, d, and d. And let's just start with this. Let's say points in the next period state. Right. So Vx prime naught is going to be equal to the u for not replacing. That's going to be just the minus the cost function, and the cost function is given here. Let's say v of x naught. That's minus the cost, which is 001 times the x, right? 001 times x times the cost parameter. And the cost parameter is, of course, self.c from here. That's the cost. That's the Vx naught. Vx1, so the deterministic part of the choice-specific value function in terms or in case of replacement, that's going to be self-replacement cost, right, in capital letters, minus the same thing minus the cost, but now this should be multiplied with 0. Right, because rather let's do it this way. Let's take the first element of this function. It will be 0, but let's do it more accurately. So let's say cost is given by this. This is maintenance cost, and this is maintenance cost of the 0th element that we need to take. Okay, and here it's going to be m cost the whole vector. Now, if we're not replacing, then the v, we're calculating this vxd, vx naught, vxz is going to be equal to the minus cost plus beta ev, beta expected values. So self beta times the expected value from the previous iteration, which is ev naught. That's the expected value passed to the Bellman operator. Okay, so if we're not replacing, then this is going to be the vector of Vx naught for all x's, apparently. Okay, and this is a constant, a scalar, this is a vector, and now we have to say self beta times EV, and here's the trick, right? Because this is for the replacement choice, then the future is described by this one point in the expected value function, which is the expected value of the new engine. Okay, so we now have the two components that enter into the log sum function over here, and let's implement this trick. So we want to take the maximum. So let's say big M equals NP maximum of Vx naught Vx1, and the log sum is then simply NP log of NP exp of Vx naught minus M. Oh, I should say M plus NP exp of Vx1 minus M. All right, this is the log sum function. So we are moving up. Oh, there's this expression as well. This is the log sum function calculated for each point of x. Now we want to for each point of x, which now represents x prime, right? So each point of the x prime that we have the log sum function now. Let's think now to calculate the expected value. This is a matrix. Can we do matrix multiplication to get what we need here? So in other words, if we have the transition probability matrix like this, with this band of non-zero elements, and in the log sum, we have a one-dimensional vector corresponding to x prime 1 and so forth, x prime n. Here we have x's, here we have x primes. So what we need to do, and what we need is for every x, we want a probability between x and x prime multiplied with this value. So in other words, we want this vector to come here as the column. And then this matrix multiplication will give us the needed sum of the transition probabilities from a given x to the given x prime multiplied with this values corresponding to x primes. So all we need to do actually is to convert the log sum vector into a column vector and multiply the transition probability with that column vector. I hope it makes sense. So what's the transition probability? We saved it into TRPR, and this is a matrix. We want to multiply that as a matrix, so therefore this add sound symbol. And then we want log sum to be the column vector. So let's add another dimension to it. New axes. And this is going to be EV1, right? Because now we've done everything that we need to do here. We've calculated the log sums and we've calculated the sums. Oh, this is a typo, by the way. This dx is here left from the integral, but because this is a sum, we don't need any dx. All right. So this is the EV1. Okay, and once we've calculated this, we can calculate the choice probabilities. The probability, and that's, remember, is it stated here? No, it's not. So that would be the last slide of the previous lecture. here, the choice probabilities are given by the logit formulas, where the we need to use as instead of the x's, right, the values of different options, we use this expected values. Sorry, not the expected values, but the deterministic components of the choice-specific value functions. Okay, so what are these deterministic components? Well, that's just, again, the utility plus the discounted expected value. The utilities we already calculated, and the discounted expected values. So essentially, we just have to do this for the just calculated EVs. That's what needs to be done. So let's reuse these expressions. M cost, this is calculated on the grid of x, but now this grid is going to represent the current x, not x prime, but the current x. And yet the formulas are the same, except now we need to use EV1 here and the EV1 over here. Everything else is as it should be. So recompute VXD for current period choice probabilities. These are both vectors, right? And so the choice probability is going to be exp of one of them. What should we choose? Vx, say the choice probability to replace, divided by exp of Vx0 plus exp of Vx1. Now let's divide by Vx1 everywhere. So we will get minus under the exp Vx1 plus 1. So I've divided the denominator by 1, and here we just get this. Okay. Of course, this needs to be in P. We need brackets down here. And this is going to be the choice probability to replace. Right? And correct. Bracket is correct as well. Okay. This is the choice probabilities to replace calculated for the points x of in the current period. All right, so that seems to be about all. Now, the only thing is that we're taking the exp here of the difference. Well, that's what we should do, right? If Vx0 is much larger than Vx1, then we may run into some numerical issues. But because we're taking the differences already, I guess we should be fine. All right, let's try to run this. By the way, let's maybe try to test the previous feature of recalculating the grid. So look, I've initialized the model with n equals 10. Calculated the transition probability and printed all of these, and then just changed this to 5 without reinitializing the model, and the transition probability updated. Okay, so this machinery with the attribute setter works. Let's now check the Bellman equation. So we say print model Bellman. And now Bellman needs some inputs, right? The EV0. Should we just give it zeros? How many? Well, model.n. And here's what we have in return. Well, maybe let's calculate EV and choice probabilities. Syntax. So what do we have? Let's start with EVs. EVs are returned as the column vector. And is this okay? Is this expected, first of all? Well, as we are computing this matrix, yes, that's totally expected, except that I would probably remove one of the dimensions, because EV here that comes in here, that's probably one-dimensional. And so we can ravel numpy returns a continuous flattened array. So when we need to flatten to one dimension, that's what's a useful thing. So here here are the expected values in after one iteration of Bellman equation. Okay, let's look at the choice probabilities now. The choice probabilities seem to be a matrix, which is not right. Should it be a matrix? No, it shouldn't. So how did that happen? Vx naught, that's how. mcost is a vector, but CEV1 here is a column vector. So we should actually flatten it over here so that it comes into the formula as a flat, as a flattened array. Okay, and so here we are. These are the choices to replace, and as you can see, the choice probabilities are pretty low. Okay, let's go to a standard specification of the model. Well, it's even harder to understand, it seems, so let's go back. And let's try to make sense of this. So we are running one iteration of Bellman equation, starting with zeros. So we are essentially only comparing the utility functions here. We, I guess, don't need this anymore. Let's add some labels. Okay, what if we start changing? So as you can see, the probability of replacement is really low. What if we start changing the parameters? So our C is 11 now. Let's change it to 1. Oh, you can see that the probabilities of replacement have jumped up really well. So that makes sense. The cost is 2.5. The maintenance cost, if we make it, say, 10, well, the replacements don't change, but the value function went down. So it seems to be working fine so far. I would say the model as we, the Bellman equation as we code it up, it reacts to the parameter changes in the predictable way. Let's move on and look at the solver for the VFI solver for this model. And as I think I mentioned before, what we have here essentially is a successive approximation solver, which we can start at any values of the EVs and then apply the Bellman operator so many times as to achieve convergence. So I'm just going to use the code from the corresponding exercise or lecture, was it? It was in part 22. I think we had a nice solver for successive approximations with plots even, didn't we? So let's reuse some of this code. I don't need this. So I'll just first paste it over here, the solver, and then print me, and here's, let's try to run all of these, run all cells. Oh, okay. It was one-dimensional, but still, that's fine. Let's work with that. Using this solver code, let's put it into the class itself, and let's say solve VFI, value function iterations. Solves the Rust model using value function iterations. Now it will be an attribute of self. Do we need to supply the initial point? Probably not. We'll just start from zeros or something. Tolerance is important, max iter is important, callback is important. So let's see what happens here. Let's say EV naught equals NP zeros. Like, are we doing that here? Yes. Except now it needs to be self. Oh, and by the way, when we are outside of the setter and getter property, we can use n just as fine, because when I say self n, what's going to happen is that this function will run, but it will just return the internal n as before. So this is the this can be the initial for VFI loop. Now we want to loop at most max iterations. EV1 is going to be self Bellman of EV naught. So X and X is now in EV. That's all it is. Iter are X, let's say EV1, EV naught. Although we will get the choices as well, right? So maybe we can send choices to the callback function as well. Error tolerance break, and here we need to say EV1, let's wait for the next iteration. Return EV1, and let's return PR1 as well. That's that should be it. So now let's call model not Bellman but solve VFI. And now this is going to be a solution. Let me keep that previous code as well. Hopefully it's going to be a solution. Well, it seems to have worked. How can we check whether it makes sense at all? It seems to have converged, so it doesn't say that there are any problems. It would be nice to actually give it some at least printing callback. Let's look at this. just to see what's actually going on. So print me iteration, EV, and error. Let's say EV1. Bellman got an unexpected. Oh, so I haven't been calling the solver. That's silly. Has no attribute, solve VFI. Okay, now we're getting the errors which I expected on the first run. Object cannot be interpreted as an integer. P0s of NP0s. No, that was not done correctly. Only size 1 arrays can be converted to Python scalars. What's being converted? Right, it's just the printout that doesn't work. All right, so let's forget about the EV and just print the error. So here we go. But what's wrong now? The truth value of array with more than one element is ambiguous. Oh, really? So the error doesn't work, but I thought that we allowed for the EV0 and EV1. That's very strange. Tolerance is definitely a scalar, right? Error is a scalar as well. Of an array with more than one element. Where does this array come from? Am I reading the message correctly? It says over here that the true value of an array with more than one element is ambiguous. Okay, let's just print this. See multiple elements. Huh, look at that. How is this possible? Check. The error is 1, the tolerance is huge. The tolerance is a bunch of different zeros. How? Where does the tolerance come from? It comes from here. Probably comes from here, right? So when we say solve VFI, remember that was the argument for calling Bellman, but now it becomes the tolerance, which is now the vector here. Here's it's an interesting bug. So now it should work fine, right? And the check is just okay. So let's delete this check. Failed to converge in 100 iterations. Does it converge at all? 3. Okay, so let's say beta is equal 0.5. Now it converged really fast. The standard value here for the beta is 4 nines, and I think we've mentioned that already, that the closer the problem is to the closer the discount coefficient is to 1, the slower it converges. So no surprises there. But we get the solution and the problem converges. The last thing to do is to make some nice plots, and then we're done. Okay, I'm gonna use some code developed in already to save time, and you're just gonna enter here as the as an additional method that sets up a graph to show us the convergence of the value function and the probability of replacing as a graph with a callback, with appropriate callback that here we don't need this for this code unknown solver. Yeah, as you can see, we may actually code up, and we will in the end of the course when we talk about the estimating of this model, we will code up a different solver for the model, which is faster, much faster. Okay, so let me run this, and I want to say solve show. I don't need any callback anymore, and we get errors. I think I need to add the our standard matplotlib call here to make graphs. Okay, that wasn't it. Mod error keyword. Right. In this code here, we actually rely on the mod, which is the model. We should probably call it a model. So the idea is that as we solve, the callback function can just as well send a link to the object itself, to the outside, to the callback. And this is how it's done, right? So we want to call back with a particular keyword model and give it a value self, which is the object. And then in the callback, we can say model and then access the parameters of the model, like the grid of the model, for example. Oh, and there we are. Okay, so what do we have here? The mileage grid is on the x-axis, right? And here we have the value function. It converged, so the converged one, I think it is drawn in red. Let's see what it says here. Yeah, solution is here drawn in red, but the different iterations of the Bellman equation, of the VFI, the value function iteration algorithm, are drawn in gray. So we started somewhere here. Well, in fact, we started with 0, and the first iteration is not shown. So the second one and so forth, and then we converge to this value function. Convergence, I remind you, is the tolerance which is set to 10 to the minus 6. So the deviation between any 2 points of these last two functions is less than 10 to the minus 6. And this is the probability of engine replacement that we've calculated. And as you can see, it grows with mileage, which makes a lot of sense. We don't need this anymore. And we can print the solution. Let's look at the model with larger dimension. In fact, let's look at the original model. The parameters, the default parameters, they correspond to the Rust paper. Oh, look at that. Well, first of all, it failed to converge in 1,000 iterations. Second of all, it's so many lines that it's hard to plot here. We know what to do if the convergence is really affected by the beta coefficient. So if I just put it to 0.9, did we converge? Yes, we did. And here's the convergence plots. So remember, we started with value function at 0. This is expected value function. And then as the VFI, the value function iteration algorithm, progressed, then we've calculated all these different new lines until we converged to the solution of the model in the infinite time horizon. And here's the probability of engine replacement, which grows with mileage. And it's not linear, as you can see here. Okay, there's a MATLAB implementation of all this code, actually a lot more of the code that we will also look at later in the course in one of the last topics. But if you would rather look at the MATLAB implementation, it's also available. Okay, that's it for the bus engine replacement model for now. But we will come back to it later when we talk about the estimation of this model. See you next time.